Welcome back. So, in the last class we saw what is a free induction decay. This is basically the signal which is physically detected by the NMR hardware. Let us have a look at it once more to make it more clear. So, what is a free induction decay? So, this is what is shown here, and a free induction decay essentially is EMF which is induced in the coil when the nuclear spins start moving around. So, let me explain this more in a pictorial form. So, let us look at how we started from. So, this is the net magnetization which is now along the x axis, and this is our z axis. This is where we apply the original B0 magnetic field, and this is y axis. So, this is a scenario after application of a pulse. So, after 90-degree pulse, after a 90-degree pulse, the magnetization is lying along the xy plane in the x axis. Now, what happens is during this T2 relaxation, the molecules, the spins now start dephasing. Okay. So, this is again the x axis, this is z axis, and this is y. So, now if you look carefully at this particular vector, what has happened is this vector is now a sum of many small vectors which are all bunched together. But when they start moving away from each other due to T2 relaxation, if you now take the component of all this vector along the x axis, the components will now not add up perfectly. So, if the initial magnetization is somewhat this much, after some time the magnetization has become this much. This is because it has reduced because of T2 relaxation. So, this is a reduction happening because the spins are now moving away in all directions in this xy plane, and because of this movement the total component, the vector addition of this spin is actually now reduced. But this magnetic vector is also rotating. So, if you recollect the last lecture, I mentioned that we have the spins which are moving in a spiral manner. That means, the net magnetization is actually moving in a spiral manner. So, if you now visualize, it has reduced in intensity, but it is also the net vector has moved away from this axis. So, it has come somewhere here and it has come to this. This is basically showing this particular motion. So, if you again go back to this picture where it is spiraling, you can see what is happening is that the spins are oscillating in the xy plane. So, when this is the x plane and this is the y direction. So, in the xy plane, if you visualize in the xy plane, the spins are actually oscillating and slowly decrease. So, if you look at, let us say, only the x component, suppose you look at only the x component, the x component starts like this, then it goes negative minus x, then again comes to positive plus x, then negative minus x, and so on. So, this x component, if you plot the x component, it is basically showing an oscillatory behavior. But remember, its amplitude is also slowly decreasing, and that decrease is coming basically from this picture here. You see the smaller, and it is shrinking in along the x axis, and finally it is 0. So, basically this is what is shown in this. So, our FID is nothing but a projection of this magnetization along the x plane and along the x axis. So, this is what is FID, which I showed in the previous class, a previous slide, and you see what is happening here. This is basically an oscillation plus a decrease. So, we use the word damped oscillation. So, let us look at this now with this in mind. How does this one look? So, the FID is now shown in the next slide. So, this is shown here. So, we can see this is what the FID which I showed earlier. You have an oscillation which is going around. Now, at the same time there is a decrease in the amplitude, and this decrease is because of the spiraling or the T2 relaxation which I showed in the previous slide. The spins are essentially spiraling along the z axis. So, their x and y component is actually decreasing in time. So, that is shown exponential. So, this is typically an exponential decay. So, which is depicted like this. So, this is the formula. The decay is exponential in nature, and it has a time constant, means every exponential function has a time constant, and that constant is T2 here. So, that means in 1 times T2 the signal would have come by about 63%. and so on. So, this is how the exponential decay is depicted, and now this is a decay, but the oscillation is captured here. So, the oscillation of the FID is because of the rotation of the spins along the xy plane, because they are essentially precessing around the z axis. So, that precession, which is the Larmor precession, is what is shown here. So, this is basically nothing but a Larmor precession shown in a simple sinusoidal manner, the oscillating manner, and this is nothing but a simple sinusoid function, it is cosine of omega t. So, what essentially is FID? FID is nothing but a multiplication of the oscillation with the decay, and these two together is what is shown here, and that is the EMF, that is FID is the free induction decay. So, that remember the word induction is because EMF is induced in the coil because of the magnets which are moving, and this is F is free because the spins are now rotating freely in the xy plane and going along the equilibrium to the equilibrium state, and decay because of this decay factor. So, that is why we use the word free induction decay, and this free induction decay mathematically can be now written in this form. What is this form is saying? That it is basically a multiplication of a cosine function, which is oscillation, which is shown here, with a exponential decay function. So, this is what why we use the word damped oscillation. So, now this is the frequency. Now, how do we extract the frequency from the FID? So, remember FID is simple depiction of an oscillation with a particular frequency and decaying with time. So, to extract this frequency out of this oscillation, we have to use the mathematical technique called Fourier transform. So, now let us see what is this oscillation coming from. So, if you look at this formula, so what is happening is your omega is equal to gamma into B0. So, remember this is the very basic concept which we saw earlier, that the rotation, the precessional frequency of a spin is basically related to its gyromagnetic ratio into B0. But now what happens is, this is where the concept of chemical shift will come into picture. We will see more detail in more detailed manner chemical shift later, but right now what is important here is that the chemical shift is essentially a parameter which is now which is making the spins have a frequency different from gamma B0. So, suppose let us say sigma is 0. If sigma is 0, then omega is equal to gamma into B0. But many spins do not have, they have concept of chemical shift, which is a parameter which deviates the effective magnetic field from the B0. So, that means the spins do not experience all the spins. Let us say you take a molecule, we will come to the more detailed structure later, but let us say you have taken a molecule like ethanol. So, ethanol has CH3, CH2 and OH. So, each of these hydrogens CH3, CH2, OH will have a slightly different chemical shift from each other, and that because of that all of them do not see the same B0 field. They experience a slightly different B0 field, and that is what is captured here. It says that the effective field experienced by some nuclei I is basically gamma B0 into 1 minus sigma I. So, this is what is called a shielding factor or chemical shift, or in a different ways. So, we will look at it more detail, but for now that is what is important to understand, is that this is a small deviation from the main magnetic field. Typically, it is of the order of 10 to the power minus 6 compared to, so that is why we use the word ppm, but we'll make it more strong in the later slides. But what is important to understand is this, that oscillation which I showed in the previous slide is basically the oscillation which is coming because of this factor. So, what is happening is that every hydrogen atom in a molecule will not have the same oscillation frequency. Oscillation frequency is nothing but chemical shift. So, the oscillation frequencies are not the same, and because of that we get different frequencies in the different atoms of the same molecule. So, typically what happens is we use this rotating frame concept here. So, now let us look at the rotating frame concept here. Again, what is happening is, in the rotating frame we are in this frequency. When, remember I said that when we synchronize the motion of the spins with the B1 field, what essentially we are doing is the B1 field is applied at this frequency, omega equal to gamma B0. So, in this frequency all the spins are now static because they are all synchronized and gone, but all the spins do not have the same frequency, they have slightly differing frequency because of this factor. So, this factor makes them different from each other. So, therefore, you can never be synchronized with all the spins at the same time. So, you choose a particular frequency as the reference frequency, let us say omega b 0, gamma b 0, and that reference frequency is basically your rotating frame of reference frequency. In that frame of reference, now different spins will have slightly different frequencies. So, let us take an example analogy again of a train, let us say is moving at 100 kilometers per hour, or let us say we have 3 trains, one is moving at 100 kilometers per hour, one is moving at 105 kilometers per hour, and another one moving at 95 kilometers per hour. Now, let us say we go into a frame of reference of the train which is moving at 100 kilometers per hour. So, in that particular train reference frame of reference, you will see that the train which is moving at 95 kilometers per hour is actually moving at minus 5, 100 minus 95, it is moving in the negative minus 5 because you are faster than that particular train. The other train which is moving at 105 kilometers per hour is now plus 5 kilometers per hour. So, you see now with respect to you, which you are at 0 kilometers per hour, because your train is essentially sitting, you are on resonance with your train speed. So, you do not experience the movement of your train, but the train which is moving next to you with 95 moves at minus 5, and the train which moves next to you is 105 moves at plus 5. So, this is called the rotating frame of reference, where you keep your frequency aligned with one particular frequency region, one peak let us say, and that peak becomes 0 frequency because it is no longer having any frequency, it is static. But with respect to that frequency, all the other frequencies are now no longer 0, they are either positive or negative. So, this is the concept of chemical shift, offset, and different terminologies which we will use later. But what is important from an FID point of view is now this FID, which I showed in the last slide, consists of oscillations. And what is this oscillations they are coming from? The oscillations are coming because different atoms in the same molecule are having different frequencies. So, therefore, they will have different oscillations, and all these oscillations are captured together in a single FID. So, that is what is written here, that the FID, what we are doing essentially is we are taking a reference signal which is some frequency omega b 0, gamma b 0, and that reference frequency is subtracted from all the frequencies, and what you essentially get is finally the subtracted frequencies. This is again the same analogy as a train, that if I have a train moving at 100 kilometers per hour, I subtract the speed from 100, so that train becomes 0, but a train which is moving at 95 kilometers per hour becomes minus 5, and train which is moving at 105 kilometers become plus 5. So, with respect to the reference, I get negative, positive, or 0. So, that is what happens in same in NMR, that you take a reference signal, you subtract that frequency from the FID, and what remains in the FID is the remaining oscillation, which is because of the chemical shift. So, if you have a positive deviation or negative deviation, or it can be 0. 0 means the signal, reference signal, is exactly the same frequency as your spin, and therefore, the spin does not experience any oscillation in that frame. So, remember again, it is all frame dependent. So, we are always using what is called rotational frame. So, NMR, the whole NMR technique is built around this concept of rotating frame reference. So, now let us come back to this FID now. So, once I subtract, so this is what is written here, the frequency of precession in the rotating frame of reference is the signal is subtracted from the reference signal. After subtracting, you will get an remaining oscillation. So, this oscillation is now after subtraction, because it is because of this chemical shift, and it is slightly different from the reference signal. If it is same as reference signal, it would have been 0, no frequency, but the fact that it is slightly different is because it is many spins may not have exactly the same as reference, and they will have an oscillation. So, this is the free induction decay after subtraction from the reference. Now, this FID, this is now further digitized. How do you digitize this? Digitization is what again the components we will see during when we come to the hardware part of it, the course. But what is happening essentially is that you take at every equal intervals of time, you take the points. So, you get basically points, instead of recording this, collecting the signal as a continuous wave, it is recorded in a discrete manner by collecting points, by discretizing at different points. So, by doing that, we use the word digitization. So, we are digitizing the FID but from a mathematical perspective, one does not have to worry about the discretization. We can think of it as a continuous wave. Now, if I do a mathematical technique called Fourier transform, will give me the frequency of this peak. So, Fourier transform is something which we will not be able to go into detail in this particular course, but it is recommended that you can refer to the books. In many of the NMR test books have very basic introduction to Fourier transform, and they also give different ways to do Fourier transformation and what is the effect and so on. So, for this particular course, what is important to know is that you have a signal which has a frequency. So, this is a time domain signal. So, we use the word time domain because we are capturing the signal as a function of time. This is what is done by the hardware electronics, which is part of the whole instrument, and that basically captures the signal as a function of time, and this signal is now Fourier transformed to get the frequency, and that is called a spectrum. So, NMR spectrum is now a frequency domain spectrum. So, you see the frequency is written here. So, what basically we are getting now is a frequency. So, this frequency means there is we can say that this FID contains a frequency omega in the rotating frame. So, again remember the concept of rotating frame is very important. We are not looking at the signal as such, we subtract it from the reference signal and then do a Fourier transform, and in the rotating frame, that is the spectrum which you normally see in all your day to day life or during the analysis, these are all in the rotating frame, and then the frequency is basically the frequency of oscillation. So, this is fine as far as one frequency is present, but remember I gave you an example of a molecule. Let us say we have a molecule which has two frequencies present. So, example is methanol. Methanol is CH3OH. So, it has two types of hydrogens, one is CH3, the H of the CH3 and the H of the OH. So, there are two frequencies. Now, in the reference frame, both will, let us say we keep the reference at the center of the two. So, let us say that CH3 has one frequency omega 1 and omega 2, I keep at the center. So, therefore, the CH3 will have a particular oscillation with respect to the reference signal, and the OH will have another oscillation with respect to this reference. So, you can see the frequencies are not same now because they are now two different atoms and two different atoms in the same molecule, and therefore, they have two different frequencies, and these two different frequencies also have different amplitudes. You see the height is also not the same here and here. That is because this particular frequency may, let us say, come from 3 hydrogen atoms. So, 3 times the signal of this may come from 1 hydrogen atom. So, you see that is the difference in NMR. Everything, all the signals, all the atoms contribute to the FID, but the contribution depends on two parameters. The contribution depends, number 1, on the frequency of their oscillation, and second thing, they depend on their number of hydrogens. So, in the case of a methanol, again the CH3OH, your H3 has 3 hydrogens. So, this particular frequency of CH3 will be 3 times stronger compared in the terms of amplitude, in terms of this height here, will be 3 times bigger than compared to OH peak, which has only 1 hydrogen, but frequencies are different, 2 different frequencies. So, what you actually capture, the hardware which captures the signal, it captures the total of these two. So, if you combine these two as a simple addition, you will end up something like this, which is just a schematic diagram showing the combination of these two signals. So, this is what is actually captured by the hardware, and now how do we from here find out the two frequencies which are present. So, this is what we know later, but in the initial stage we only have this FID with us, which has a mixture of two signals, or it may be many signals, we never know. We have to do a Fourier transform. So, when you do a Fourier transform of this particular FID, this will now it will give us immediately two different frequencies. So, this is the beauty of Fourier transform, that it captures the frequencies which are present in this time domain FID, and that is represented in the frequency domain spectrum. So, if you see here now, the intensity of this peak is now directly proportional to the number of hydrogens here. So, in the case of methanol, we discussed that there are 3 hydrogens. So, this could be 3 times stronger. So, this signal will be 3 times stronger compared to this. Of course, in this picture it does not look like so, but as a qualitatively you can think of it that this particular thing is 3 times this, basically depends on the number of hydrogens. So, if you have 4 or 5 or n number of hydrogens, this signal will directly be related to the number of hydrogens, whereas this also similar. So, this is how a spectrum is recorded. Basically, you record a time domain FID and then you then combine. The FID is automatically combined because that is how the whole signal will be detected, and upon Fourier transformation, which is typically done by the computer automatically, and that will give you a spectrum. So, you can look at this in the same molecule. Let us take an example of ethanol. In ethanol, you have CH3, CH2 and OH. So, you can see here there are different hydrogens. This is one hydrogen, this is another kind of hydrogen, and this is another. And why do we say there are 3 different hydrogens? We will look at it in a later time, that is based on the chemical shifts. But the point here to take home from here is that there are 3 different hydrogens here, and each of these hydrogens has a particular oscillation, because this will have a frequency, this will have a different frequency of oscillation, this will have a different frequency, and when you subtract from the reference, they will have this particular frequency shown schematically here. Now, this frequency which is shown here is nothing but a multiplication of the cosine function of that is oscillation of the CH3 group with the exponential decay of the CH3. So, this is what is I showed in the previous slides about what is an FID, and similarly here this will be now a multiplication of the frequency of B, that is this hydrogen H2 with its decay, which is shown in this FID, and that decay is now depending on the CH2 T2 relaxation. So, T2 relaxation of this hydrogen need not be same as the T2 of this, which need not be same as T2 of this. So, generally we can assume a different T2 for each of this. Now, for OH similarly you have a frequency of OH oscillation multiply with the time domain, that is the decay of the OH signal, which is now captured here as a T2 of OH. So, these 3 together will combine, and you can see the total FID now whatever you capture by the hardware is now a combination of all the 3, because the hardware does not distinguish between different oscillation. All it can see is oscillations, and oscillations can come from anywhere of all sources, and all of these together are added together, and what is given to the computer is essentially these 3 FIDs added together. So, you see this is what the signal comes, and this will look a very strange signal because it depends on this factor, this factor, and all the different factors. And not only that, one factor which is not shown here is the number of hydrogens. So, number of hydrogen is 3 here. So, this signal will be 3 times stronger compared to this signal, which is let us say 2 times compared to this signal. So, 1:2:3. So, that particular thing is not shown here, but you have to keep in mind that the FID is not only simple addition, it is addition of again the amplitudes, in the sense it is a weighted addition of the amplitude, because this will be 3 times stronger compared to this compared to that. So, this is how an FID is captured, and when you do a Fourier transform will give you an NMR spectrum. So, this is what is shown here. These 3 frequencies are basically the 3 different oscillation which we saw in the previous slide, coming from CH3, CH2, CO. This is what is shown here. If you go back in this manner, we can see that this is mathematically coming because there are 3 terms here. Each term contributes to the different peaks here. So, this is the spectrum. What is shown in the bottom is basically a spectrum. A spectrum consists of a frequency axis, which is the x axis, and your y axis is your intensity. Now, remember the intensity is basically proportional to the number of hydrogens. So, there are 3 hydrogens. So, this will be 3 times. But again, one thing is, before we look at the height of intensity, when we talk about intensity in NMR, it means the area. So, suppose I take an area of this peak here. This is like a triangle. This is actually in reality it is not a triangle, but let us say it is like a triangle. If I take area of the peak here, that area will be 3 times the area of this peak here. So, this will be 3:1 ratio. And now, this one, which is CH2, will be 2 times the peak of area of this peak. So, you see the area is what is important in NMR, not just the peak height. The peak height has a different connotation. What is important is the area of the peak. So, the peak area is basically proportional to the number of hydrogens. So, if there are 3 hydrogens, this peak will be 3 times, let us say 3x, and this is 2, this is 2x, and this is x. So, 1:2. So, area is very important in NMR, as we will see later. This is where the quantification aspect of NMR comes into picture. The whole quantification depends on the area of the peak. So, we look at area to decide how many hydrogens are there and what is the concentration. For example, if I take a mixture of ethanol and methanol, so I take a mixture of 2 different molecules, and if these are 2 different concentrations, the areas of the peaks of ethanol will be proportional to its concentration. Area of peak of methanol, which is also in the same sample, will be proportional to its concentration. So, therefore, directly by comparing the peak areas in NMR, we can actually figure out or find out the concentration, of course, provided we have a reference concentration, which we will see that later how the reference etc. is done. So, summarizing this whole aspect, essentially we have will repeat this, that there is a molecule, let us say ethanol, which has 3 different hydrogen atoms and therefore 3 different oscillations or 3 different frequencies or 3 different chemical shifts. So, chemical shift was briefly introduced, but we will come back to chemical shift at a later point. So, the chemical shift nothing but what is the frequency of a particular hydrogen atom. So, you see there are 3 different frequencies, which are 3 different shown here, and each one has its own decay constant, which is given by T2 relaxation, and this decay constant now is all multiplied with the frequency. So, these are 3 different signals which are added together, added in the sense we do not physically add them, it is automatically captured by the hardware, because all 3 come at the same time and they are represented by a simple addition, and this addition upon Fourier transform gives you different peaks, where the height of the area of the peak is proportional to the number of hydrogen. So, this is how a basic Fourier transform addition is done in NMR to give NMR spectrum. What we will do now is we will move on to the NMR hardware in the next class. We will see how all this hardware is built, how the spectrum is recorded, how does the spectrometer look, what does the magnet look like, and then after that we will come back to analyze how a 1D spectrum can be interpreted.